Okay, well, I see there's lots of chatter here going on, so there's probably questions about the homework. Oh, we need to. So, do we have questions about the homework for today? What assignment is this? Assignment 3?
Yes.
And I got your other ones back to you and with solutions. But so, any questions? For exercise 32, unfortunately, I don't have my book. But what's your question?
32, you're basically making a table of pi. You're trying to get the pi notation?
Yes. Oh, the pi notation, right. So let's go back to that. We can look at.
Isn't that this one?
Well, I mean, it's basically you're focusing on the zeros.
Okay, so look, figure 10.25 shows how to do the pi notation. So the truth table is the truth table.
Yes.
And by the way, I notice a few people when you do truth tables are not being careful to do them in the right order. When you write a truth table, always do it in the order ABC 0000001010011. And so, in other words, in numeric order. All right, just that's the standard. But then the way you write it in pi notation is everywhere there is a 0 in the truth table, it's that number. It's the decimal number of the binary pattern for ABC.
Okay. When you're optimizing it, though, when you're optimizing.
Oh, did I ask you to do an optimization in an OR of ands?
Yes.
Oh, I did? For today?
Yeah.
Oh, we need to see how to do that. I didn't think that was coming until next time. My assignment is a little out of sequence with this. Let's talk about let me show you how to do that. Here's a dual Karnaugh maps. Yeah, I was going to do this today anyway, so we'll just do it now. All right, now, so here's the thing about dual Karnaugh maps, you guys. To minimize a function in an or and expression, what you do, it's analogous to the way you write an or and expression by working in the and or space and then converting. So in fact, it's exactly analogous to the way we did this Boolean algebraically. So here's what you do. You take the complement of the function and you minimize that the same way we normally minimize it as an and or expression. And then we use x equals x prime prime, in other words, double negation, and De Morgan's law to actually write it. So now let's do an example. Actually, I think one of the examples that we did before, I think, wasn't it, did we do this one? Did we do this Karnaugh map? Have we minimized this Karnaugh map? Does that look like a familiar pattern? Maybe not. Maybe we didn't do this. Maybe not. So here's A, 0, 1, and here's BC, 0, 0, 0, 1, 1, 1, 1, 0. Well, let's go ahead and minimize this. Here. This is an interesting problem. Let's go ahead and minimize this one.
Okay.
So tell me, how do we cover this one up here?
It's BC.
We cover it
Yeah, vertically.
vertically like this. And how do we cover this one?
Horizontally.
Horizontally. So this is like this.
And that'll be AB. So
All right.
AB or BC.
So man, see how easy, how quick you can do this? Mm-hmm. So does everybody see here that what we have is x is, and this one is BC is 1, 1, right? And it spans the A rows. So this one is BC or what? And this is going to be A something, right? A what? AB? Now, is everybody clear on that? Does everybody see that that's what that is? Right, that's just normal and or. This is an and or circuit. Actually, well, no. Okay, we'll do this in a minute. All right, is everybody with me on this? Right, so now the way you do an or and is you take the same function, only instead of doing it, what you do is you minimize its complement. All right? So here, we're going to minimize its complement. Well, tell me, what is the complement? What is the Karnaugh map for the complement? What is the complement do? What is the complement of a function?
Just put
Everywhere there's a, yeah, the complement is, turns a 1 into a 0 and a 0 into a 1, right? So if this represents the truth table, if this represents the Karnaugh map for x, the Karnaugh map for x prime would look like what? Would be 1, 1, 1, 1, and 1 here. Are you with me? Does everybody see how that? Are we focused here on the right? Okay. Is everybody with me? Okay, so if this is the case, tell me, how would you minimize? Suppose I said, now minimize this using a Karnaugh. How would you do it?
the B prime.
Well, I mean, where would you do the groupings?
Oh, the 4, the box, the whole box.
Yeah, you do this group. And now this one, we can't group it with a neighbor over here, and we can't group it with a neighbor over here. But what can we do? Pac-Man effect, and group this with what? With this one.
Yeah, A prime, B prime.
All right, is everybody clear? And the way we indicate that on a Karnaugh map is like this. And so now let's write down what this is. X prime with this Karnaugh map, well, what's this group right here? That's the group. It's not going to have an A in it because it spans the A row, so that's what? It's B prime, yeah? Good. Or, now what's this one? It is the A prime row, and then C prime are the outer two columns, right? Because of the 0, 0. So it's, what do we say? A prime, C prime. Are you with me? So this minimizes the complement. But now what do? We say x equals x prime prime. And now we do a little Boolean algebra. So what is that? That's B prime or A prime C prime prime.
De Morgan.
And now we use De Morgan and we say this equals, now we can also do double negation, right? So this is going to be B and, so this is going to be B and,
A or C.
now this is going to be
A or C.
A prime, C prime, quantity prime. Are you with me on that? But A prime, C prime, quantity prime is going to be what? A or C. Yeah, it's going to be A or C. Are you with me? And sure enough, this is an or and. This is an and or. But now look, you guys, here's an interesting phenomenon. This is an interesting phenomenon. Let's draw the circuit for this.
Okay.
So what do we have? Let's go ahead and literally draw it.
2-level circuit?
Two-level circuit, and or, so let's do the and. And so what's coming in here?
A B and a C.
B, C, and then what's coming in here for this and? An A and a B, and then these are going into a what? Into an or, like this, and this is coming out. Now is everybody clear on this circuit is doing this? But now what about this circuit? This is an or and, right? But, so what's the or?
A or C.
A or C. Is everybody good with this? So here we have A or C. But then that is anded with what? Just B. So now this is anded with B. So B is just coming in, well, we don't even need to draw the line that long. This is just coming in with, B. So now tell me, you guys, this is the minimum and or circuit. This is the minimum or and circuit. So what do we have here? Two, how many gates do we have here? We have two input ands and a two input or. Here we only have what? One two input or and a what? Two input and.
So space-wise, it's bad.
So actually, this illustrates a fact that to do all of these problems 100% thoroughly, you actually have to minimize, you would actually have to minimize both the and the or and implementation, because one of them might be better than the other. Okay, so here's figure 10.29c and 10.39 shows this, and here's what we just did. And it illustrates the fact that, you know, you actually have to do both. You have to do the circuit and its, well, you construct this dual and do it, and then do this algebra, and you might get a minimum in one case that's better than the other. So now, I didn't realize that was due today, but that kind of question, but so you see how to do that now? Are we good? All right then. Okay, now you guys, let's do this. Watch this. Here in figure 10.30, we have a Karnaugh map, and how many input variables do we have?
3.
3. A, B, and C.
Let's do 4.
Let's do 4. How many entries does a truth table have with just 3 variables? It has 8. So with 4 variables, it has 16. Are you with me? But now the cells have to be arranged in such a way that if each term differs by 1, then that other term has to be physically next to it, adjacent to it in the table. So look, you guys, what's the pattern here? It's for the BC column, it's 0, 0, 0, 1, 1, 1, 1, 0, right? So now instead of having,
Same thing down the left.
it's going to be the same thing down the bottom, but in going down to the bottom, it's also going to have to be what? 0, 0, 0, 1, 1, 1, 1, 0.
Are we going to have AB on the left and CD up top?
Yeah, we'll have AB on, yeah,
Okay.
yeah. Okay, so you anticipated correctly. So look, you guys, here it is, figure 10.33. So we have AB on the left is 0, 0, 0, 1, 1, 1, 1, 0, and then CD going across the top is 0, 0, 0, 1, 1, 1, 1, 0. And so look at the pattern, you guys. If I give you a problem, the next assignment, homework assignment, has the sigma notation, because I don't want to just, we don't want to take up space drawing big 4x4 tables, you know. So in sigma notation, the numbering, so now look how the numbering goes. The numbering across the, you know, as you go in a given row, going across the column is the same pattern we had before. 0, the first one is 0, the second one is 1, then 2 is way over to the right, and then the 3 is the next one to the left of that. Are you with me? So it's 0, 1, and then 2 over here, and then 3 over here. And then the second row is 4, 5, and then 6 is on the right column, and then 7 is to the left of it. But now what happens is you do what? You skip a row. Do you see how the numbering goes? Mm-hmm. You skip a row. So this is 8. The 8 is the lower left. Mm. Do you see how that works? That's cool. So you should see how to, you know, you should be able to go, you know, I mean, if you just do it with your finger, it's 0, 1, 2, 3, and then 4, 5, 6, 7, and then the bottom row, 8, 9, 10, 11, and then the third row, 12, 13, and then 14, 15, like that. You just see the pattern. You know, this is like doing your pin on your phone. You know the pattern of you don't even have to remember the number of your pin on your phone, right? You can just know that it's up, down, left, boom, boom. You just know. So I mean, that's how you just know that's the counting pattern for a 4x4, for a 4-input Karnaugh map. And here what we have are the regions where the variables are 1. So look. The bottom 2 rows are where A is 1. You see that? Are you with me on that? And then the middle 2 rows are where B is 1. Yeah? Mm-hmm. And then the right 2 columns are where C is 1. And then the middle 2 columns are where D is 1. You're going to have an A, B, C, D. All right? Okay, so now let's do a few. And so you know, the minimization, it's the minimization is the same thing. You want to cover, you know, as many as you can, you know, with a few. Every time you do a grouping, what kind of term is that? Every time you group them, that's one.
Term.
Yeah, not necessarily a min-term.
Right.
In fact, we hope it's not a min-term. We hope,
that's right, so it would be all four.
a min-term would have all four.
Right.
But anyway, it'll be a term, an and term.
Right.
So each grouping will be an and term, and then however many you have, you OR those are ORed, right? So here, let's do a few, see if we get some practice. So don't peek if you're viewing the slides, no fair peeking. Okay, so let's do 1, 1, 1, 1, 1, 1, 1, 1. Okay, so here's here's AB, 0, 0, 0, 1, 1, 1, 1, 0. And here's CD, 0, 0, 0, 1, 1, 1, 1, 0. All right, hop to it. That includes you guys out there, video land. How would you, what do you think? Have an idea?
0, 0, 0, 0 to 0, 0, 1, 0. And then same on the bottom.
Wait, can you tell me which?
Top left corner.
The top left corner
Top right.
and the top right. So like a Pac-Man effect here?
Up there and at the bottom.
So two Pac-Man effects.
Yeah, two.
Oh, whoa. Wait. Do you mean two Pac-Man effects like this and then like this?
Could you do all four?
Yeah, ha. Yeah, this is incorrect. This is an incorrect minimization. Because this one is adjacent. I mean, you could also do the Pac-Man effect this way and the Pac-Man effect this way, right? Because this one is adjacent to this one. Because what is this? This is 1, what is this one? 1, 0, 1, 0. And what is this? 0, 0, 1, 0. So these differ only by 1, right? But now you anticipated it correctly. That is an incorrect minimization. Instead, what we should do is what?
Full square.
Yeah, the way you draw that is like this. You do it like this. That's how you draw it. Does everybody see that that's one grouping? Okay? And then what?
Just that one tower.
And yeah, and then this one right here. Okay, so now let's draw. Now let's write down the expression. So x equals. Now what were the corners? B prime. Now where's B? B. Yeah, the B. Here's where B is 1, right? These two rows are the B rows. So the top two rows are the B prime. Yeah, that's the B prime rows. So that's B prime.
And then the far out.
Wait. If it was just B prime, it would be these whole two rows.
Right.
So it's
And
B
B prime,
prime. Yeah, it's B prime, C
D
prime.
prime.
D prime. Oh, right. B prime, D prime. Is everybody clear on that? Does everybody see how that works? Because D, the two outer columns are where D is 0. So that's B prime, D prime. Now how about this one? This one's easy because it's a column. It's just what?
It's exactly that. Yeah.
C prime D. Yeah. Let's see if that. Did we do it right? Here's figure 10.34. Did we do it right?
Mm-hmm.
B prime, D prime, or C prime D. Yeah. All right. Is everybody good? Okay, let's do another one. These are fun to do. But once we get to 4 variables, though, it can get a little tricky. So let's do another one. Okay, so here's AB 0, 0, 0, 1, 1, 1, 1, 0. CD 0, 0, 0, 1, 1, 1, 1, 0. And let's put ones here, 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 and here.
Could you group the bottom two with the top two?
Oh, that was a great insight. That's the one that most people don't see right off the bat.
Or,
Did you hear what she said? You can actually, you can do a Pac-Man effect here with this up here. That's what you were saying, right? Yeah, that's excellent. So we can do these two with these two like that.
And then you do the far right corner. Pac-Man.
Pac-Man these?
Yep.
Don't write this down. It's not correct.
or could you include them with the,
Because, yeah. Now, why isn't this
You
correct?
can do a 3x3 square.
No, you cannot do 3 by 3. It's got to be 2, 4, or 8.
Could you ever do a row of 3?
No, you can't do it. It's got to be 2, 4, or 8.
Oh, you just said that.
But this is incorrect, yeah?
Because that's 3 input, right?
I mean, we could write an expression for this, but what I'm saying is that this minimization is not the correct minimization. Somebody said it, what the correct one was.
don't you want me to go Pac-Man the other direction to the other side?
Why cover, we need to cover both of these, but we want to use as big a grouping as possible.
Oh, so you can just do another square.
Well, why not cover this and this at the same time we cover this and this? That will make this group bigger. Tell me, what term would this be? What term would this one correspond to?
That would be
This would be what?
C.
It would be a 3.
It would be a 3 input
B prime C D prime.
B prime C B.
B prime C D prime.
Yes, it's B prime. This would be B. Yeah, this would be B prime C. Good. This one would be B prime C D prime. Are you with me? But on the other hand, if we do what? Instead of doing it like this, if we do what?
The full square.
The full corner Pac-Man, If we do this and do it with this, now it's not B prime C D prime. Now what is it?
What it was before, just B prime D prime?
It's
No, I mean C prime D.
no. What are the four corners?
B prime D prime.
Yeah, the D prime are, yes, D prime is this,
And B prime.
and B prime is this. So it's it's B prime D prime. So now instead of being B prime C D prime, it's B prime C prime. And this is a what?
No, D prime.
Oh, sorry. B prime. Yeah, right.
It's a 3 input and now it's a 2 input.
Yeah, the previous one was a 3 input AND, but now we can do it with just a 2 input AND, and that's better. Is everybody clear? But we still have one more to go.
It's just the 2.
Yeah, and of course, we don't want to just do this by itself. If we did this by itself, what would it be? It would be
A prime B.
A prime B, C prime D. But why do it that way? We don't have a neighbor here or here or here, but we do have a neighbor up here, so we can do this. So what is our x then, our minimized function? X is what? B prime D prime, or now what is this? This is the first 2 rows are A prime, yeah? So it's A prime, C prime D. A prime, C prime, D.
You forgot one still.
This, the other square.
Oh, wait, that was the, oh, wait, what?
The
Okay, we have
first
the-
square.
Oh, we did the first, oh, yeah, we need to do these. Yeah, which one are those?
That's
What are these?
Or B prime, C prime.
B prime, yes, B prime and C prime, yes. So let's count, let's name the gate, or we won't bother to draw it, but let's name the gates. What, how many? Two-
It's going to be
Two,
input,
2 input ands,
1 3 input,
1 3 input and,
and 1 3 input or.
and 1 3 input or.
Now let's do the or and of this.
Well, yeah, you know, and to be complete, I mean, to be completely sure, we would have to do, you know, you have to know how to do that, but that takes kind of a long time, and so frequently I'll just say minimize the and or. But you need to know how to do the other one also. Okay, does everybody see how that? Did we do it right? There's the figure 10.35. Okay, good deal. Okay, let's do another one. Now how about this? Okay, now let's do 1, 1, 1, 1, 1, 1, 1. We're going to make a point here. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0. This one's kind of obvious, but there's an interesting phenomenon that goes on that this will illustrate. So, gang, so group, how should we group?
The whole first column.
The whole first column.
The whole first column, I think, is a good idea.
The two middle of the third column.
The two middle,
Two middle rows of the.
like this one?
And then that last remaining one with either the left or the right.
Well, the fact that this could be grouped with either the left or the right is an interesting fact, because what does it say about the minimum? It's not what?
Unique.
It's not unique. Are you with me? So let's go ahead and do it with this. If we do it with this, what's the expression for the function? X is what? So what's the left column? It's C prime D prime. Or, now let's do this one over here.
CD.
No, there's more than that.
There's more than that, because
So,
CD would be the whole column.
CD.
Are you with me?
BCD.
BCD.
So it's where B is 1. Yeah, so it's BCD. Or now let's do this grouping, which is row what? AB, right?
ABD.
So that's AB, and then where D is 1. So it's ABD. Right? Is everybody clear? Okay. But on the other hand, yeah, so that's this. All right? But on the other hand, in figure 10.36, part A, that's one possible minimization. But on the other hand, what we could do is, instead of grouping this with this, and here I'll just, so I don't have to rewrite the whole thing, we'll just erase it. Okay? And we'll do it this way, because this is also covers them all. And the thing of it is, and what is this function? Well, in this example, with this grouping, X is C prime D, or BCD, or, but now instead of being ABD, it's what?
ABC prime.
It's AB still, AB, and then C prime, that's where the C is 1. So it's ABC prime. Right? So that's another possible minimization. It's the exact same number of gates, same number of inputs. You might argue a little bit that, well, this you need an inverter for C, but you need an inverter for C here anyway, and so, you know. But we are ignoring the inverters in our minimization. So everybody, are we good? Okay. All right. Now the next one is quite interesting, I think. And it looks like this. All right. And now this one, again, no fair peeking. Watch this. We're going to do 1 across the top row, and then 1s on the last 3 of the second row, and then a 1, 1, and a space and a 1 here, and a 1, 1 here. All right, you guys, this one illustrates a really tricky situation. So let's just try to do it kind of systematically.
Can you group 6 together?
You cannot group 6. That was a good question. You cannot group 6 because if you group 6, there's no way to write a term for that.
Can't group 3,
See,
can't group 5.
yeah, because see, the terms come from the intersections of the regions, and there's no way that you can intersect, you know, regions and have 6. Yeah.
Can you group? Oh. Yeah, just like doing the bars together. But
Well, I mean, the thing of it is that you have, it's legal to cover a 1 with more than one group, and you know, and you want, generally, you want to use as bigger groups as possible, but because the bigger groups that you use, the fewer groups that you will probably need.
right.
Now watch this. So watch this. Let's just think about it for a minute. Let's concentrate on this min term. What is this? 0, 1, 2, 3, 4, 5, 6, 7, 8. 8. Let's look at 8
Okay.
at this one. Now obviously we don't want to do we can't do a Pac-Man effect over here, right? Because of this. Okay? So it seems pretty obvious, and we can't do like the whole left 2 columns. So it seems pretty obvious that to do this, one way to do, the biggest group that we can use to include this is what? Are these 4. Is everybody with me on this? So look, it seems like,
AC prime.
yeah, we'll do the letters in a minute. Okay? And now, what about this? What about this one? Which is number 0, 1, 2, 3, 4, 5. This is number 6, I guess.
Do a column, or you could do,
Well, we can't do 3. We could do a column. We could do it with these 2, but why do it with these 2 if we wanted to do what?
or you could do a square.
Yeah, we could do 4. We can't do the row because 2 rows, the complete 2 rows because of this, right? But we could do the square. In fact, that's the biggest one. Are you with me? The biggest. Hold on. The biggest. Oh, maybe you saw what's coming up. The biggest group that I can use to cover this one is what? Let me tell you. The biggest. I mean, do you agree that the biggest group that I can use to cover this one is this? I mean, isn't that true? There's no bigger group that I can use to cover this one. So that seems plausible, right? And now, how am I going to cover this one? What's the biggest group that I can use to cover this one?
That whole row.
The biggest group I can use to cover this is 4. The biggest group I can use to cover this is 4. The biggest group I can use to cover this is 4, and this will do it. All right? Well, but it's irrelevant because if you Pac-Man this with this, it's in this group anyway.
Well, I meant, up, down.
Oh. Well, yeah, you could, but, oh, that just means it's not unique. That would just be covering, because this one's covering these two. If you did Pac-Man this way, those would be covering these two instead, but the same ones would be covered. Oh, yeah. Okay. And now what? Now, what's the best way to cover this?
Do a group of 8.
What's the best way to cover this? Can we do a group of 8? I don't think we can do a group of 8.
It would be, you're right. It's
No, I don't think we can do a group of 8.
You can.
Now, what's the best way to cover this?
A full square.
You could either do a full square here, or you could do a column or whatever. But anyway, there are 4, right?
Right.
So that would be the full square here. Okay? And now, what about this? It can't cover it with here. There's no neighbor here. There's no neighbor here.
Baby column.
I guess you could either do what? A Pac-Man here, which would be 2, or just this one,
It's also 2.
which is also 2, right? So now, what we did seemed plausible.
There's,
What we did seem, now why does this seem plausible? Do you agree that this is what makes this tricky. Do you agree that every one is covered with the biggest possible group?
I agree.
That's true, is it not? And do you also agree that if you take away any group, you're going to have one not covered?
No.
Wait, you mean one of these? Which group can I take? Oh, wait a minute.
Top right.
You're right. We could take away the top right group. Oh. Yeah, that's right. So we didn't, yeah.
That's what I just.
But the reason, oh, yeah.
'Cause it
Yeah,
was
so we could take away the top right group.
take whole term.
Yeah, because we did this one first. Yeah. Okay, well, that was a good observation. Right. So now it's all now it's really messy, and I'm not sure how to do this without just going to the next slide. But okay, so let's
It's fixable, yeah.
take this out. We can just take this one out like this.
Perfect.
All right. And now let's write down the expression. So what's this bottom left group?
AC prime.
AC prime, yeah.
A, yeah, that's where A is 1, and C prime. Yeah, so this is A, C prime. Now, what is this group? A prime, D is right. And now what's the top row?
A prime, B prime.
A prime, B prime. And now this one that is the smaller group has more inputs. So what is this? B, C, D prime.
Cool.
Yeah. Okay. So what we had was a plausible but incorrect solution. And now here what you, oh, actually we came up with a different one, right?
Yeah.
Actually, what we came up with was in figure 1038. Oh no, this is even different yet. What did we come up with?
No, but he.
No,
meant-
no,
he meant before
that-
we erased it.
We came up with a different one
We
now.
created, yeah, with a different.
No, I think this one is not part B of figure 1037, is it?
Yeah, it is.
Yeah.
Oh yeah, it is.
But what we have.
Oh no, yeah, you're right, it is.
Yeah, but what we had before was
Wasn't
different from A.
Oh, what we had before was different from A. Oh, I led you down the different. I led you down a different primrose path.
That's okay.
Do you see what I'm saying? I should have.
You made it easier for us.
I did make it easier for you. The plausible but incorrect. No, actually, here let's take a look at figure 10.37a. A plausible but incorrect solution. Now, why is that one plausible? Yeah,
Because in
shoot,
this
I blew it.
one,
Because with this
If you
one,
take any of them out.
if you take any of them
something will be
out,
left behind.
something will be left behind. Yeah. I didn't remember how to do that. I didn't remember how to do it incorrectly to
Illustrate a point.
to illustrate a point, exactly. Anyway, do you see figure 10.37a? So how did we do that? We did the
We did a vertical bar instead of a
we did a vertical bar. Yeah, if I had done a vertical bar here, then it would have been a little more misleading. But you see the point, right? But now just to show you though that another illustration of the fact that the minimization is not unique, look at figure 10.38.
That's a good one.
This is a really nice one, isn't it? It's the exact same. It's the exact same Karnaugh map, but it's covered. I mean, it's the same function, but it's covered differently. And see how neat that is. You got the C prime D column, the second column from the left, and then you've got somebody actually mentioned. I remember in our discussion doing these four, these four here, and then having this one be a Pac-Man with this one, and then having these four be all by themselves. But that's the same minimum. It's the same number of gates, right? 3 2-input ANDs and 1 3-input AND, and 1 4-input OR, which is the same number of gates as this. So it's not unique. Now. So your assignment for next time, and then we did the dual Karnaugh maps. You could also do the dual Karnaugh maps in with four inputs. It's the same principle. Now let's think a bit. Let's finish with this idea. So now what would happen? What do you think would happen if you had 5 input variables and you wanted to minimize the function in a 2-level network? How would you have to draw the Karnaugh map?
You'd have 2.
First of all, how many entries? Instead of 16, you'd have what?
32.
32, right? Are we good with that? Yeah, 32. So how would you have to draw the Karnaugh maps? With great difficulty. How would, but how, huh?
You'd have to go 3D.
Yeah, you could go 3D, right?
That's not good.
And then there would be the last variable would be A, B, C, D, E. So one of them would be with E being 0, the other one would be with E being 1.
Right.
And you have to stack them on top of each other. So you'd have to go right in 3D, And then maybe, I wonder if you could do a cube. I don't know.
A cube is like
Well, you could do them right next, but then how do you draw them so that they're physically, because see, the corresponding ones have to be physically next to each other. You would have to know that the corresponding ones, like you would have to know that the upper left corner of one was next to the upper left corner of the other one. Or you can do colors, that's another way to get a third dimension.
Rectangular prism.
Yeah, I'm saying it
But
could
then,
be
yeah,
a cube
32.
until you have 6.
Yeah.
It's actually an interesting question. It's actually an interesting problem, and the fact that we live in a 3-dimensional spatial universe, makes this work for 4 variables quite nicely if you do this Pac-Man thing. In fact, the fact that you do this Pac-Man thing means really that there's what? If we were able to wrap, if
Kind of like a sphere? Or like a
actually, what is it? Could it be a
parallel pipe?
or a torus? Or that would be a 3 variable. Well, anyway, it's an interesting question how you would do that. But so guess what? Guess what exists? Back in the 1950s, 2 computer scientists by the name of Quine and McCluskey actually wrote an algorithm that is able to solve this problem with a program. Did you ever? Because what is? Oh, by the way, we should know this. What is the fundamental question of computer science? It's what can be automated. So what did Quine and McCluskey do? They automated this. But think of how tricky this one was. It would have to, you know, it would have to work for all those cases. And furthermore, it works for any number of variables. You can Google it and see what it's like. So up to 4 variables, the Karnaugh map way is the way to go. And there's lots of practical, you know, digital circuits that, you know, you can whip out a 4x4, you know, 4-input Karnaugh map and do some useful. You can do useful design with a 4x4 Karnaugh map. But anytime you get, you know, to 5 variables or more, then you just do it with Klein-McCluskey. Do it algorithmically with the program. But the thing of it is that Klein-McCluskey program, unfortunately, it's NP hard, which means it's not polynomial. It's not big theta of n squared or n cubed or n fourth. It's big theta of, like, it's exponential. So it gets really, you know, by the time you get to, you know, more than, you know, yeah, 20 or whatever, then it gets really hard. And so there's another algorithm. There's another algorithm that is an approximation algorithm that's good. You can research that. But this stuff has all been, they did that, the Klein-McCluskey, they did this in the 1950s. So you see, because this is when all this digital stuff was first being, you know, developed, and all these questions were all open. Oh, they were all open questions at the time. But now it's a standard part of our toolkit. You know. Yeah, pretty neat, huh? All right. Hey, we've got Martin Luther King on Monday, so I'm not going to see you guys till Tuesday. All right? Good deal.
Good deal.
See you next time.